should be 1. 1 over tau is equal to K ut, where tau هنا is represent RC, and which is also in second. لأنه RC هنا meter times meter square per second. This is for R, and C is the meter square. So we simplify and find the unit of tau is second. So these are the first order system, some examples of the first order system. When we obtain a model for a dynamic system, we need to apply some test signal to see if the system performs according to certain design specification for the design system. In general, we require that the system to be stable. We want the system to be fast, and we want the system to be steady state error is small. So, Shabab, here, what do we want? If we look to this system, if we take this one, suppose you want to design thermometer like this one, which measure the temperature. This is called thermometer. This is, you want to design it. Thermometer. You want to design this one and see how it performs. Suppose we have the room temperature is equal to 23 degrees Celsius. This is the time, and this is the temperature. The room temperature is somewhere here, 23 degrees Celsius. When you design your thermometer, and you bring it to the room and see if it is measuring the temperature right or wrong. So normally your measurement will do something like this. It starts from 0, and then it goes like this, and then it will be somewhere like 23 or like 22.8 or 22.7 or 20. So here we see that the error is small error. This is what we want. If, for example, the room temperature is 23 degrees Celsius, and your thermometer give you a reading of 50 degrees Celsius, 50, what do you do with this thermometer, Shabab? What are you going to do with it? Can anybody answer me? So your room temperature is 23, and your thermometer that you have designed give you 50 degrees Celsius. What are you going to do with this thermometer? Any answer for me? Any answer for me?
Throw the thermometer.
Just throw it. As simple as that. So
calibrate, Doctor.
Yeah, we will talk later on how to calibrate. But as the first one, it does not satisfy of the requirement, which is what small error. It's not satisfied. This is not satisfied. صح? If your thermometer, Shabab, will behave like this. Now the thermometer from here to here, the time from here to here, how much time you do expect from here to here? Time from here to here. What is the time do you expect to give you? Yani when you put it in the room, you should wait for how long to give you the temperature? What is the time you can wait for?
10 minutes.
10 seconds.
10 seconds, maximum 1 minute, let's say 2 minutes, up to 5 minutes, مقبولة. But after that, you cannot wait until قيام.
Yes.
You cannot wait for hours. So if it does not satisfy this requirement also, that's why we are saying it should be a fast response. It should be a fast response. Now, the second condition is a fast response. We should not wait for a long time. Fast, very fast. So we have said small error, very fast. Now, it should be stable. What do we mean by stable here, Shabab? Stable, we means that if the system, if you design your system and your temperature, we said it's somewhere here, 23 degrees Celsius, we do not expect our thermometer to read like this. It increases with time. It is increasing with time. So if it is increasing with time, it means it's not stable. It's not stable. So you want something that go directly like this. With time, it should go and to the steady state value. You want it to be like this one here, and then it goes like this. The blue line. بينما the red line is not stable. So you want it stable. So it has a bounded output or a bounded reading. Is this clear, Shabab? So these are basically the criteria that we want in our system dynamics and control. I hope everything is clear here. Other performance criteria may exist, but we will be mainly concerned with the above mentioned three. Usually the actual input to dynamic system is unknown in advance. However, by subjecting the system to standard signal, now we know, Shabab, we know that the standard signal, like we said, the impulse or the pulse or the step response, they have the first order system has certain behavior. The second order system has a certain behavior. Suppose you bought a device and you don't know your device with it, whether it is a first order system or a second order system. So to know the system of your device, you just plug in to some unknown signals like the step input, like the impulse input. Specifically, the step input is the most used one because it has a drastic characteristic. It goes from 0 to, it jumps to one value. So here we use this one. If it behaves like a first order system, we say, oh, our system or our device we bought is a first order system. Otherwise, it will behave in another order that you can characterize later on. This is, we can do it also by saying that this is system identification, which means you identify your system, how it behaves. Is this clear, Shabab? Any question before we move? Any question, Shabab? Okay. If it is clear, let's move to the next slide, Shabab. I will not spend a lot of time on this slide because I already explained this, and I told you when you have an LTI system, that is supposed input is a force and the initial conditions. So first of all, you neglect the initial conditions and see the response to the force term. This is called the force response or the particular response, and it will give you this. And then after that, you take the forcing term is equal to 0 and take the initial conditions, see the response that is due to the initial conditions. And we call this one, when you studied the differential equation, you were calling this one the homogeneous solution. But here now we call it natural response of the free response. So it's called natural response or free response. After that, Shabab, we do the superposition principle because we are dealing with the LTI system here, LTI system. We do the superposition principle, so we add the response due to the forcing term plus the response due to the initial conditions, and then we got this one. I think I showed you here an applet from MIT website how this one works. And also after that, I mentioned to you when we have a damping, the homogeneous response that is due to the initial condition, after some times it died. And we have only the steady state response or the general solution that is due to the steady state response. لأنه the initial conditions or the homogeneous part will die with time. We also mentioned this one, if you remember. So I will not spend much time to this one. They are the maplet, as here you can see them, the applet, both of them. You see where we can see them. I showed you how this one works. Now we go to the typical signal that we can use. We have the impulse signal that is defined by delta. Delta is equal to 0, one time is different than 0, which is here 0 and here is 0. But delta is equal to B, the magnitude here is B. One time is equal to 0. This is the impulse input. We have the step input that is commonly used in dynamic system because it represents a sudden change in the value of the reference input. And then you can see it is 0 when time is less than 0. And all of a sudden it jumps to B is equal to B. The magnitude is equal to B here. So we can use delta T is equal to B. And remember, Laplace transform of the impulse is B. بينما Laplace transform of the step input is B over S here. The ramp input or the velocity input is called also velocity input. It occurs where the input has a constant rate or increase with time. Constant velocity. Then this one is you can consider it as the displacement. The slope is B. The velocity will be constant like this. Constant velocity here. So this one also ramp input we can consider it. We can also we have the parabolic input. The ramp input, you remember, Laplace transform for it is simply B over S squared. And we have the parabolic input or constant acceleration. Parabolic input is given by half BT squared, like it is shown here. And 0 one time is less than 0. And Laplace transform for this one will be simply B over S cubed. So we will have our first order system, and we will apply this input to this system. So how we are going to proceed is like this. This is the sinusoidal input, but I will show you now, this is the first order system. We are going to write it like this. This is, let's say, K over S plus 1 over tau. This is our first order system, and this will be our output. Output, how it behaves. We don't know this output, but we will put some signals. We will see the step input, the impulse input, like this. And then we will see the ramp input, like this. And we will see the pulse, if you want, or any other parabolic input anyway. So for each one of these, we will see what will be the output. What will be the output? What will be the output? What will be the output? This one, when you have sinusoidal input, this has spatial attention, and it will be in details, it will be given in details in chapter 9, because we will study the behavior for it in chapter 9. So this one is given step or impulse here. This is the ramp, and this is the acceleration input. And for each of these, we will see what will be the output. So this is what we are going to see. With impulsive load also, we can see the impulsive load. For time, which is the impulse, we are given the Laplace transform of the input for the pulse is B. And now we characterize the first order system equation, or in general, the first order can be written like this: A0 y dot plus A1 y is equal to A2 u of t. This is in general the most general case. So now if we take the derivative is equal to 1, here should be 1. So if we divide by A0 to make the derivative is 1, we will have A1 over A0y plus A2 over A0u equal u of t. Where here, شباب, you should know, يهديكم الله يصلح بالكم عبد الله. A0, هنا we should know, شباب, y naught is the output, y dot is output, and u t is the input. U is the input. So we can write it y dot over 1 divided by A0 over A1y is equal to A0, A2 over A0 u of t. We try to bring it into the standard form, which is y dot plus 1 over tau y is equal to k u of t. Now, if you compare these two equations here, this one and this one, we will see the following. We will see that tau is equal to A0 over 1. Tau will be this one, this amount. And K, capital K here, will be simply A2 over A0. So this is the standard equation for the first order system. All the previous equation, if you remember when we did the introduction for this lecture, I showed you how we they all fall into this category. Either it is electrical system, mechanical system, whether it is rotation or translation, liquid level system, they all fall under this category, which is first order system. So now, if we take Laplace transform of this one, we can say S y of S for this one, plus 1 over tau y of S is equal to K U of S. And if we take now the transfer function, which is the output over the input, will give you J of S is equal to Y of S over U of S, which is K over S plus 1 over tau. So we can write it in this form. U of S is the input. Y of S is the output. We have the transfer function. This is the output. Now, basically, this is what we are looking for. What will be Y of S for this first order system for a given input. The input, you remember, we mentioned them. Either it could be impulse, either it could be step, either it could be any other function. So we have two quantities. We have two quantities, which is the input. We have the input. We have the transfer function. We need to find what will be the output Y of S. So is it clear our objective, Shabab, what we have? So we have the input, given signal, known signal. It could be impulse, it could be a ramp, it could be anything. We have the transfer function, now K is here. And then we are looking for the output response. But you should remember that the first order system, if somebody tells you what is a first order system, the things that the first order system is characterized by its gain K and the time constant tau. Always gain K and time constant tau. These are the two factors that characterize the first order system. Now, if we look to the free response, U of t is equal to 0. يعني ما في input. Input is due to initial conditions only. Initial conditions only, Shabab. Now, if we take Laplace transform of Sy of S, this should be equal to Laplace transform of Sy of S. Now, I will write it here, Shabab. Laplace transform of Y dot will be equal to Sy of S minus Y of 0. This is because the initial conditions. واضح? This Y of 0, it is minus on the left-hand side. So if I take it from the other side, it will be Y0 now. Y0. That's why it is Y0 here. And now, S plus 1 over tau will be common. So this is due to the initial conditions. Y0 is the initial conditions. If you look now, you solve for Y of S. Here you solve for Y of S. You will have Y0, S over 1 plus 1 over tau. And if you take the inverse of Laplace transform, it will be Y0 exponential minus t over tau. So the response, your response of the first order system will be decreasing exponentially. And the limit of this term, when t goes to infinity, this limit will go to 0. It will go to 0. And exponential minus infinity, it will be 0. That's why you have here, they are all going to 0. They are all going to 0. Here, Shabab, we have the values of tau. We have changed the values of tau. And we have Y0, we put the initial conditions, Y0 is equal to 1. So all the curves start from this point. This is the initial condition. This is Y0 is equal to 1. Now we are varying the values of tau. Tau is equal to 0.2, tau is equal to 0.5, tau is equal to 0.7, tau is equal to 1, tau is equal to 2, and so on. So when tau increases, the value of tau increases, exponential minus 1 over tau decreases, and it will be slower. So that's why the smaller the value here of tau, the fastest response you will see. The response will go faster to 0, to the steady state value. So if you increase tau, e exponential minus 1 over tau, it will be larger and it will get slower. So you increase the value of tau, see how it is going to the steady state or to the 0 value. Is this clear, Shabab? This is for the free response, which means the initial conditions only. Is this clear? Is it clear, Shabab? Any question? Any question, Shabab? So now, هنا Shabab, if you remember, also we are varying y0, but we are fixing tau. Tau is fixed, is equal to 0.5. But we are changing the initial conditions. Here, initial conditions is equal to 6. Here, initial conditions is equal to 3. Here, initial conditions is equal to 2. But you can see we are fixing tau is equal to 0.5 in this equation. We are just changing y0 and plotting. Y0 is changing. Here, y3, here, y2, here, y1.5, and so on. So, but we fixed tau. The value of tau we fixed. It is 0.5. Any question? So the time constant, Shabab, how do we find the time constant for the system? I explained this, if you remember. When you get this equation, the time constant is the value for time that makes the exponent equal to -1. This exponent, exponential minus t over tau, would be equal, minus t over tau will be equal to 1. So here, if we take exponential minus t over tau, exponential minus t over tau should be equal to exponential minus 1. So this exponent minus t over tau equal, to have it equal -1, we need to have minus tau over tau. So t will be equal to minus tau. You simplify this with this, and the exponential will be equal to -1. So we should have exponential -1, which is equal to 0.368 or 36.8%. Make the exponential equal to -1 and you are done, which means that at this value of tau, when the time is equal to tau, the response fall to 36.8% of its original value. If the original value is y0, at this value of tau here, the response fall to 0.368 or 0.37. This one equal to 0.368 of y0. This is the value of tau. So tau is the time constant, and y of tau, it is 57% of the original value. For also, we are interested in finding the value of 4 tau. The value of 4 tau is at 98%, which means 0.02%. Y of 4 tau will be equal to 0.02 y%, which is converging to the steady state value or to the zero value here. That's it. How sometimes I ask the students in the major exam, I will give them a response and I ask them to define from the response, define what is tau. All you have to do is to draw a tangent here at the origin. If this is your plot, if this is your plot is behaving like this, you draw the tangent here at the origin. At the origin means at this point, you draw a tangent like we are doing here. The tangent line here. The tangent line here, when it goes, when it is here, it means this one is tau. From here to here is the value of tau, or from here to here is the value of tau. Well, Shabab, this is the value of tau. If you now draw a perpendicular line, it crosses the response y at a point. This point corresponds to 37% of the original response. If the original response starts at y0, so this one represents 0.37 y of 0. If the total distance from here to here is y0, so the distance from here to here will be simply 0.37 of y0. Is this clear, Shabab, how to find the value of tau? take the exponent is equal to -1, or you draw a tangent line at the origin. At 0, you draw a tangent line and you will find your time constant. Now, Shabab, if you have an impulse for a first order system, remember the impulse is simply given by this B delta T. And if you remember, the Laplace transform of the impulse is simply B. Now, if you take the output, if you remember, we wrote the equation, or we wrote the original equation for the transfer function. We wrote the transfer function of this form. When we got this, we wrote it in this form. This is our transfer function. So now we are given this equation. We are given U of S. So we can say from here, we can say that our equation Y of S, I am writing here, Shabab, either from this, or either from here, or from here. We can say Y of S alone, Y of S, will be equal to U of S, times this one, K over S plus 1 over tau. This is plus. شوفوا شباب, don't in any way, this is G of S, the transfer function. This is the input and this is the output. Now we know the input, whether it is constant or it is an impulse or whatever it is. The transfer function, we have it. So we are looking for this equation. We are looking for the output. So if we have now this one, U of S is an impulse. For the impulse, this will be B. U of S will be B. And then all we have to do is to find the transfer function or the response for this equation. This is what we have here. If we have B, so our equation will be U of S times, this is the transfer function, this is the transfer function. So it turns out to be substitute U of S by B. So it will be BK over S plus 1 over tau. BK over S plus 1 over tau. If we want to take now the inverse Laplace transform for it, Y of T will be simply equal to B of K. This is a constant, BK, and then exponential -1 over tau T, which look exactly like the initial condition. Here, in the initial condition, we have this Y of 0. So this is what do we have? Constant, or BK, times exponential -1 over tau, which is T, where C here is equal to BK. So it is exactly the same response like the BK. So here, when tau goes to infinity, exponential -1 over tau will be equal to 1, and your constant C will be equal to 1, or BK. So the value here is simply BK. And then, as you can see, tau is equal to 0.5, we have this, tau is equal to 0.1, we have this, and then the smaller the tau, the fast is the response, the 0. So this is the free response, looks like the impulse response exactly in the same way. Now, if we take the response to first order system, we have I remind you, the input U of S is like this, B. This is a step input. This is the time is here, U of T. And this is the time here. Now, Shabab, U of T is this one. So U of S will be simply B over S. So if you substitute B over S in your equation, remember, this is the transfer function, was our transfer function. This is U of S, you substitute it by B over S, because B over S is the step input. So B over S multiplied by the transfer function. So if you look here, we have two poles. S is equal to 0, and S is equal to -1 over tau, which you can write in partial fraction. If you write it in partial fraction, it will be A1 over S. This one can be written like this, A1 over S, plus A2 plus S plus 1 over tau. All you have to find is A1 and A2. We found them. We found that A1 is equal to K tau. This is A1. A1 is here. And A2 is equal to minus BK tau. So at the end of the day, you take this one will be BK tau will be common between the two. You take it out, and then the inverse Laplace transform of 1 over S will be 1. And the inverse Laplace transform of S plus 1 over tau will be simply exponential minus 1 over T tau. And if you look here, if you draw this response, it will behave something like this one. From 0, it will go up to when T goes to infinity. When T goes to infinity, this term will go to 0. This term, exponential minus tau over T, this term will go to 0. And then you have the limit will be BK tau. This one you can find it using the final value theorem. When you use the final value theorem, you will find that this is the steady state value, or the value when the time goes to infinity. This is the response for a first order system due to step input. So when we have a step input like this input, so typical behavior will be like this one. It starts from 0 and then it will go to the steady state value. We need to find what is the value of tau here. What is the response at the value of tau? In a similar way, we draw either the exponent is equal to minus 1, or we just draw the tangent at the origin. If you draw a tangent from here, this is the tangent. This is the tangent line. The tangent line, Shabab, it crosses the steady state line. This is the steady state line, steady state line at a point, at one point. So from this point here, you draw a vertical line like this. This vertical line gives you the value of tau here. At this value of tau, the response is at 63% of the final value, 63% of the final value. If from here to here we have B tau, B A tau, so at this value, when T is equal to tau, the response is at 0.63 BK tau. And this is known as the response for a first order system. Any questions, Shabab, before we move? Any question? So this is what we have here now. This is the input as a summary of the slides. This is the input. The input is given by a step with magnitude B. The transfer function is given by a first order system, and the response is behaving like this. Remember, so this one will be always the response of a step input. So at step input here, the step input, this one will be, the response will be at 63%. At 2 tau, the response will be like this at 0.864, and here value will be 0.864. If you draw here the value perpendicular line here, this corresponds to 86%, like this, or 86.5%. At 3 tau will be 95%. At 4 tau, the value at 4 tau, it will be something like 98%, 98%, it approaches. So this is the line 100%. So this is the line 100%. So this one will be at 98% of the value. At 5 tau, when you go 5 tau, the response reach 99%, and so on. So this is the behavior of the first order system to a step input. And the way to find the time response is to draw a tangent line here. It crosses the steady state line at a point. You draw a perpendicular line. It crosses the x-axis at one value called the time constant. This corresponds to 63% of the final value. Or you put the exponent, exponential minus will be equal to -1. These are some responses that have been drawn for different tau. This is we're fixing the bk tau. Here we are putting b is equal to 5, k is equal to 1. These are fixed. And then we are changing the value of tau. Tau is equal to 2, tau is equal to 1, tau is equal to 0.7, tau is equal to 0.5, tau is equal to 1. So which means increasing the time constant here will give you a fast response. If the time constant is small, it means it's taking too much to go to the steady state response. شوف الerror هنا كم. This is what you are expecting to get, and see your response, where is it? It's far from the input. Here, when you increase the value of tau, you are approaching, the error is becoming smaller. So the value of the time constant, if you increase the time constant, you go faster and faster to the response. So increasing the value of tau slows the response. The 63% line is of the ultimate value is here. This is the tau value. And this curve is tau is equal to 8, not that it passes 63%. The ultimate response is at tau is equal to t. So as we mentioned here, the time for exponential -2 to decay to 37% or to 36.8% will be this one. Exponential equal to -1. When exponential -1 is equal to 0.37. So here will give you the time constant will be equal, if you equate this y of t, if you equate it to equal at time t is equal to this tau, you will get 0.63 bk tau. So if you look now to the poles, how they are located, we have one pole is equal, s is equal to 0, and another pole is equal to s is equal to minus tau. If you draw it in the imaginary or the complex plane, you have this is the real axis, this is the imaginary axis, and s is equal to -1 over tau is the real value. It's located on the real axis. So steady state error in ESS is equal to 0 when it goes to the final value. This is what do we mean? This is the response, and then there is no error here. You will see that there is no difference. Steady state error is equal to 0. E is equal to 0. Now the system is stable if this one is equal to bk tau, and we define this one to be b tau. And provided we have the s is equal to -1 over s lies on the left-hand s plane. لأنه هنا this one, if it is here, will have an exponential that is having a negative exponent, exponential -1 over tau. When you find the Laplace transform of this one, it will be exponential -1 over tau. So as long as the pole is here, is on this left-hand side, you don't have any problem because this will be converging. It will be converging to a value. When the problem rises here, if the pole is located here, the pole is located on the right-hand side plane, so this one will be equal s -1 over tau. Exponential -1 over tau is equal to 0, gives you s is equal to 1 over tau. And this will give rise to exponential 1 over tau t. 1 over tau t. Exponential 1 over tau t, with time it will increase like this. It will be increasing, it will be non-stable. So provided s is equal to -1 over tau lies on the left-hand side plane here, on the negative side, so we have a stable system or finite value of the system. I will stop here, and then we will continue, inshallah, next, bi'idhnillah. Any questions, Shabab, before I take the attendance? So let us see who is with us today. العلوة منير معنا. العلوة منير. يا منير. منير. دي غلبي موجود؟ دي غلبي.
بس موجود يا دكتور.
اهلا وسهلا. المسعودي عبد العزيز. الملا ماجد. الملا ماجد. ماجد. القحطاني حسين.
موجود يا دكتور.
اهلا وسهلا. يحيى عباس. I think اليحيى هي dropped. يحيى عباس. المحمدي عبد العزيز. عبد العزيز كيف لك اليوم؟
خير الحمد لله. كيف دكتور؟
يحيى عباس dropped. القحطاني عبد الكريم. عبد الكريم كيفك اليوم؟
بخير الله يسلمك.
الشهري أحمد. احنا كنا زمان نقول اليوم آخر يوم وبكرة نشبع نوم، اليوم آخر يوم وبكرة نشبع نوم. ما عندكم هذه، انتم الحصة بتاعكم بعد الظهر يعني ما عندكم مشكلة. هاني الرميح. الشهري موجود؟ علي الشهري. علي الشهري. الرميح هاني موجود؟ هاني معانا اليوم. قرني علي. علي أهلين قرني. فارس
موجود.
أهلين زهراني. أهلين. الحمدان عبد العزيز. شيخ حمدان. حمدان عبد العزيز. بعض الطلبة أخذوا فسحة يمكن. شريدة محمد. الشريدة محمد. حمدان عبد العزيز موجود؟ ما هو موجود. العجمي مبارك.
موجود العجمي مبارك يا دكتور.
سهلا.
أهلا بك.
طليحي يوسف. يوسف. الزاير حسان. أهلين حسان. الجهني نادر. الجهني نادر. الجهني نادر ما هو موجود. العقيل رائد.
اهلا وسهلا. هلا والله يا دكتور.
مين العقيل؟ كيف حالك؟
الله يجمل حالك. كيف حالك انت؟
مين وياك ان شاء الله. الحمد لله. درويش عبد الله.
حاضر.
اهلا وسهلا.
اهلا.
وينك يا عبد الله؟
موجود.
حسين موجود؟ شرفونا. ايوه بسمعك. شرفنا حسين.
حاضر دكتور، كيف حالك؟
اهلين وسهلين.
الله يسلمك.
الدبيس علي.
موجود الدبيس.
اهلا وسهلا. المحمدي سلمان. يا سلمان. المحمدي سلمان. البشر علي.
موجود دكتور. موجود يا دكتور.
الجارودي حسن. لسه محمد الرشودي ما ناديتك لسه. الرشودي محمد. اوكي. هاشم ناصر.
حاضر دكتور.
أهلا.
هلا.
العواد سلطان. اهلين. سوبدي علي. عبد اللطيف. اهلين عبد اللطيف. عبد رب النبي موسى. اهلين شيخ موسى، كيف حالك؟ الزهراني عبد العزيز. العتيبي فهد.
حاضر دكتور.
اهلين فهد لك اليوم. المحمدي يزيد. يزيد محمدي. يزيد يزيد. الخباز منتجب. الخباز منتجب. منتجب الخباز، أهلا وسهلا. الصبحي نايف. الصبحي نايف. يا شباب مين ما سمع صوته يقول لي من جديد، يمكن
يس دكتور مين يوسف
أخذته غفوة والله منا. خلينا نعاود اللي ما سمع.
يس دكتور.
لحظة. الحمدان عبد العزيز حضر. يوسف الطليحي. لحظة يوسف. نعم مش تبغى يوسف؟
ما سمعت صوتي يا دكتور.
لحظة شوية بس دقيقة. بالواحد أنا أنادي بالواحد ده. الحمدان عبد العزيز موجود؟ لا ما هو موجود. 1. الشريدة محمد موجود؟ لا ما موجود. 1. يوسف موجود؟ يوسف خلاص أوكي. الجهني نادر. الجهني نادر. يا نادر. يا نادر. نايم شكله. يزيد المحمدي. دقيقة بس خليني بنادي بالواحد. الجهني نادر ما هو موجود اليوم معنا. المحمدي سلمان. المحمدي سلمان ما هو موجود. الجهني نادر ما هو موجود. بس مين تاني؟ مين ما سمع صوته تاني؟
أنا يا دكتور حسن الجارودي.
جارودي حطيتك حاضر. حطيتك حاضر.
شكرا.
حاضر. شكرا. مين ما سمع صوته يا شباب؟ اسمه الحمدان عبد العزيز ما جاء. اللي يحيى عباس موجود؟ ما جاء اليوم. يحيى عباس هذا حذف. طيب خلاص شباب نشوفكم على خير ان شاء الله.
دكتور
موجود؟ نعم.
درجات الميجر ان شاء الله متى راح تنزلها؟
والله لسه ما شفتها. اذا صلحتها نزلها احتفظ بها انا. اذا نزل لسه ما صلحتها
ان شاء
بعد
الله.
ما اصلحها ان شاء الله ننزلكم. الويكند تعرف خلال الاسبوع نتعب كثير. الويكند يعني ارتاح الويكند وبعدين خلال الاسبوع الجاي لكل حادث حديث. المحمدي عبد العزيز. نعم ايش عندك يا اخي الكريم؟
دكتور ارسلت لك ايميل على السؤال الثاني، نسيت اكتب اسمي على الورقه دي. رفعته في بلاك بورد. شفت الايميل ولا ما شفته؟
لا ما شفت الايميل. ايش الحكايه؟
لاني كنت
موجوده ما دام تحت اسمك انت في السيستم. دونت ووري ما عندك مشكله.
ايه لانك انت ارسلت في ايميل انه
السيستم ما عندك مشكله. ما عندك مشكله.
تمام يعطيك العافيه دكتور.
الله يعافيك. شكرا. any question شباب؟ يس نايف صبحي. يس
دكتور بالنسبه لدرجات الاختبار انت قلت ان شاء الله الاسبوع الجاي تقدر تكتب عليك يعني لو تساعدني عليها الان قبل ما اخلص الحل.
ما قلت الاسبوع الجاي نايف. ما قلت الاسبوع
لا
الجاي.
الاسبوع الجاي راح تبدا فيها.
راح نبدا اصلح.
اي نعم. بس يا دكتور ودنا نشوفها قبل ما ينتهي حذف الماده يعني.
متى الحذف الماده؟ الحذف متى؟
اعتقد نهايه الاسبوع هذا، الاسبوع الجاي.
متى هو التاريخ؟ قولي التاريخ بس.
ما اذكر صراحه بالضبط لكنه قريب يعني.
والله شوف احنا يعني بشر اللي نقدر عليه، ووقته احنا انا نبذل مجهود يعني اكثر من اللازم. تحضير اللاب، تحضير الامتحان، تحضير الكويزز، تحضير يعني الوقت بتاعنا كله في التحضير. ف we are killing ourselves يعني كمان بشر زيكم اعطونا فرصه وانتم بس جالسين وتسمعوا وبتمتحن فقط. بس انت تحضر تشوف سلايد زي هذه احضرها لك او اللاب زي هذا ياخذ مني في بعض الحين 24 ساعه عامل وتواصل. فاحنا بشر
الله يعينك والله دكتور.
فرصه يعني، ما احنا ما آلات ولا روبوتات ولا اي شيء.
صحيح معك حق.
طيب بالتوفيق ان شاء الله.
وياك يا رب ان شاء الله. يعطيك العافيه.
الله يعافيك.